Today we're going to be creating a circuit that is a bandpass filter that passes frequencies between 100 Hz and 1 kHz. We're going to do this on multisim.com. So let's get started. The first thing that I'm going to do is I'm going to grab an AC voltage source here and place that down. Now remember, a bandpass filter is a low-pass filter and a high-pass filter placed in series. So let's create both of those. So we're going to create a low-pass filter first. It doesn't really matter which one goes first, but I'm just going to make a low-pass filter first here. We're going to put that down, and then we're going to put down a capacitor. I'm going to use Shift R to rotate that around, place that right there. Then I'm going to make a connection from my voltage source to my resistor, and then over to my capacitor, and then back there. Okay. Now I want this filter to actually pass frequencies between 100 Hz and 1 kHz, like I said. The final bandpass filter should do that. So that means that I want this low-pass filter to cut off everything above 1000 Hz. Okay? And I want the high-pass filter to cut off everything below 100 Hz. So what we can do is, right now, we can set up this low-pass filter and make sure that it cuts off everything below 1000 Hz before we go on and finish making our bandpass filter. So let's do that. We want this to cut off everything below 1000 Hz. So let's do a little bit of math and figure out how that's going to work. Okay? I'm going to use Paint here just to do a little bit of quick math. So I remember that for low-pass and high-pass filters made with a resistor and a capacitor, the cutoff frequency, FC, is equal to 1 divided by 2 pi RC. Okay? Now, what I want is, I know what cutoff frequency I want. I want that to be 1000 Hz. And so I've got two variables that I can play with, resistor and capacitor. So I'm just going to have to choose one of those arbitrarily and then figure out the other one. So what I'm going to do is I'm going to choose the resistor, and I'm just going to choose ahead of time that that's going to be 1 kilo ohm. Okay? And I know that my frequency is 1 kilohertz. I know that that's the cutoff frequency that I want. So what I can do is I can rewrite this. I can say 1000 Hertz equals 1 divided by 2 pi times 1000 ohms times my capacitor. Okay. So now what I have to do is I have to solve for the capacitor. So I can bring that over, multiply both sides by that, and then divide both sides by 1000, and I get the capacitance that I want is 1 divided by 2 pi times 1000 ohms times 1000 hertz. Okay? So that's what I can do to figure out my capacitance. I can say the capacitance is 1 divided by 2 times pi times 1000 times 1000. So let's actually do that on the calculator here. I say 2 times pi times 1000 times 1,000 equals this, and then 1 over that should be my capacitance. So this is 1.59 times 10 to the minus 7th. So that's 0.159 times 10 to the minus 6th. So 0.159 microfarads is what I should have. So let's go back to multisim and put that in. So I'm going to make this capacitor 0.159 microfarads. Alright, so that should do it. So now what I can do is I can put a voltage probe here and run a simulation, and I'm going to come over here to my settings and change some settings here. So instead of I'm changing settings for the voltage. So now I click on the background to change the settings for the simulation. So what I'm going to do is, instead of an interactive simulation, I'm going to do an AC sweep, and then from 1 to a whole lot. So I'm hoping that my cutoff frequency is going to be around 1,000 hertz. So I'm going to look at the frequencies between 1/10 of that, or 100 hertz, and 10 times that, or 10,000 hertz, 10 kilohertz. Alright, so we got that set up, so now let's run our AC sweep. Okay, so that's interesting. So what happened there? So let's see. Let's go back to our schematic and see what's going on here. So we've got a 1 kilohertz, or 1 kilo ohm resistor, a 0.159 microfarad. Oh, okay. I see. Over in the error, it says no ground node was found. Okay, so that's a problem. So we need to tell it where 0 volts is so that it has something as a reference. So I'm going to put that there, and then attach that. Now let's run that AC sweep again. Alright, so that's looking better. So we can get rid of the phase, because we don't need to see that. And then we can make the minimum value 100 milli down here. So that'll be a little bit easier. A little easier to see. Alright, and now we can use a cursor to make a measurement and make sure that we're getting the cutoff where we think. It looks about right, the 1 kilohertz. In fact, we can just hover the mouse, and we see that at 1 kilohertz, in fact, the magnitude is 70.7%, which is what we're looking for. So that is looking right. So far, so good on this schematic. We've created the low-pass filter with a cutoff frequency of 1 kilohertz, just like we wanted. Now, we said we needed to create a high-pass filter with a cutoff frequency of 100 hertz. Okay, so let's do that. The way we're going to do that is we're going to create a capacitor here. Remember, the high-pass filter has the capacitor up on the top, and then the resistor on the side. Okay, and now I'm going to connect this capacitor over there, and connect the resistor up there and down here. And now I'm going to move my voltage probe over there. All right, now we need to choose the values for this high pass filter so that it has a cutoff frequency at 100 hertz. So we're going to do essentially the same thing that we did before. We're going to use the same basic equations, but we are going to use different values here. So instead of 1 kilohertz for the cutoff frequency, I'm going to use a cutoff frequency of 100 hertz. So then what I have is 100 hertz is 1 over 2 pi times 1,000 ohms times capacitance. Now I chose 1,000 ohms kind of arbitrarily. It's just a nice round number. If you find that the capacitor that you get with 1,000 ohms is really too big or too small, you can choose a different value there, but that's a nice place to start from. Okay, now I'm going to solve for my capacitor. So I multiply through both sides by C, and I divide both sides by 100 hertz, and I get C equals 1 divided by 2 times pi times 1,000 ohms times 100 hertz. So again, I'll do this out on the calculator. So I'll clear that. So I'll say 2 times pi times 1,000 times 100 equals, and then I say 1 over that, and I get 1.59 times 10 to the minus 6th. Okay, so 1.59 micro. So then we'll go back to multisim and we'll put that in. So instead of 1 microfarad, we'll make this 1.59 microfarads. Okay, so now we have a low-pass filter and a high-pass filter in series, so we should be able to have, we should have a bandpass filter now, okay? So I'm going to adjust these settings. So now the starting frequency should be lower so that I can see my lowest cutoff. So the lowest cutoff frequency that I have is 100 hertz, so I'll make the starting frequency 10 hertz, and then I'll still go up to 10 kilohertz. So let's run this again. There we go. So now, when we run the simulation, we can get rid of the phase. And now we can see that we have a nice bandpass filter. It allows the frequencies in the middle to pass through, but it blocks out or absorbs the frequencies above and below this band of filters. Okay, and we can find the so that's looking pretty good. So that's how we can create a bandpass filter in multisim. Now we're going to talk about how to create a bandstop filter that rejects the frequencies between two particular points. So for the sake of simplicity, I'm going to choose the same cutoff frequencies that I had before, 100 hertz and 1 kilohertz. But now I have to build a low-pass filter with the cutoff frequency of 100 hertz. Remember, last time the low-pass filter had its cutoff frequency at 1,000. So now the low-pass filter has the cutoff frequency of 100 hertz, and the high-pass filter has a cutoff frequency of 1,000 hertz. Okay, so I've got the components that we need here. The calculations are just the same that we've already done, so I won't redo those, but you could do them again if you needed to choose different cutoff frequencies. Okay, so what I've got here is the building blocks, and now I'm going to build the circuits that I'm looking for. Okay, so I'm going to build a low-pass filter here with a cutoff frequency of 100 hertz and a high-pass filter with a cutoff frequency of 1,000 hertz. I'm going to use this little ground connection here so that things are a little bit cleaner. All right. Now, the basic idea with a band stop filter is that you just connect these two filters together in parallel. But in practice, that causes a little bit of a problem. So let's see what happens if we actually connect them together in just that way. So if we just connect these two filters together directly like this, these two outputs, and then measure the voltage, let's see what happens. So remember, a band stop filter should allow low frequencies and high frequencies to go through, but have a nice rejection part in the middle. Let's see if that actually happens here. So that's not what we see. Instead, we see some low frequencies going through a little bit, and then the high frequencies get cut off a bit more. But it's not just a nice rejection in the middle with low and high frequencies going through. So let's go back to our schematic and try and figure out what's going on. Well, basically, what we have here is we have a circuit with two different outputs that are telling us two different things. And when we just connect those two outputs together, they end up kind of fighting with each other. So the low-pass filter says low frequencies should go through it easily. So if there's a low frequency signal, the low-pass filter voltage here is going up and down, saying, yeah, that voltage can go through. Whereas the high-pass filter says, no, that's a high frequency, that's a low frequency, we can't let it go through, it should be 0. So this one, the high-pass filter is saying 0, 0, 0, the low-pass filter is saying up and down and up and down and up and down, and they end up fighting with each other. So that's not what we want. So what we can do instead is we can put in some resistors, and these resistors allow the circuit to kind of come to a compromise here. Okay. I'm going to use 10 kilo ohm resistors because that will not load down the circuit too much. And then I'm going to take this and just copy it and put another one right there. And then I'm going to connect that to the output. All right, so now these two outputs have been connected with resistors, and we're going to put the voltage probe right in the middle. What's going on here is I think about this as kind of like a jump rope, okay? And one filter is holding on to one end of the jump rope, and the other filter is holding on to the other end of the jump rope, okay? So let's talk about those low frequencies again that we were just mentioning. So at a low frequency, the top filter, the low pass filter says, yeah, that should go through. So it's kind of taking its end of the jump rope and going up and down and up and down and up and down. Whereas the high pass filter says, no, 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 that should not go through. It should be 0. So it's holding its end of the jump rope firmly on the ground. Okay? So that one side of the jump rope is going up and down, the other side is being held still. The middle of the jump rope then goes up and down kind of halfway. Okay? It's not all the way up and down, but it's not perfectly flat. It's halfway. Similarly, at high frequencies, the high-pass filter says, yeah, that should go through, so it takes its end of the jump rope and goes up and down and up and down and up and down. The low-pass filter says no, it holds its end still, so the middle of the jump rope ends up going up and down halfway. Okay? And then in the middle frequencies that don't go through either one, both sides are kind of holding their ends of the jump rope still, so the middle doesn't move very much at all. Okay? So for the low frequencies or high frequencies, the middle moves halfway. For the middle frequencies, this part of the circuit this voltage doesn't change very much at all. So let's see if we can see that on our AC sweep. All right, so this is the AC sweep. Okay, so for low frequencies here, we can see that, let's see what the voltage is there. If we hover over that, that's 497 milli, about 500 milli, which would be half of the amplitude. So that's when the low-pass filter is going up and down and up and down, the high-pass filter is holding still. The middle point that we're measuring there is moving about halfway. Okay. Likewise, at the high end, it's also moving about halfway, and in the middle frequencies, those are getting cut off quite a bit. So this is a nice band stop filter. So this is what we're looking for. Okay. So that's how you can create a band stop filter, and how you can design it on multisim.com. Now let's talk about how to design an LC circuit. And this time we're going to choose a cutoff frequency of 100 Hertz. Now remember that an LC circuit has an inductor and a capacitor. So we'll choose an inductor and a capacitor. Now, depending on the orientation that you put these together in, you can make this a low-pass filter or a high-pass filter. I'm going to put them together like this in the low-pass filter configuration. You can tell because the inductor passes low frequencies through and the capacitor allows high frequencies to go through. So what's happening is that low frequencies from the voltage source here go through the inductor and go to the output there, where we'll put our voltage probe. And most of the high frequencies get blocked by the inductor. And any high frequencies that do make it out through the inductor also go through the capacitor and get down to ground. So this is kind of a double whammy. The two components are working together to reject high frequencies and allow those low frequencies to go through. So this is a low-pass filter. If you switched the position of the inductor and the capacitor, then you would make a high-pass filter. Okay? All right, so I've got a low-pass filter here in LC circuit, but I want to choose values so that I have a cutoff frequency of 100 Hertz. So let's do a little math and figure out how to do that. Now remember, for an LC circuit, the cutoff frequency, FC, is 1 divided by 2 pi times the square root of L times C. Okay, so what I want to do is I want to figure out a capacitor value here. Okay, so I'm going to multiply both sides through by square root of L times C and divide both sides by FC. So that gives me square root of L times C equals 1 over 2 pi times FC. Now I can square both sides and I get L times C equals 1 divided by 4 pi squared times FC squared. Then I can divide both sides by L and I end up with C equals 1 over 4 pi squared times FC squared times L. Okay? In this case, I'm just going to pick L arbitrarily. I'm going to choose the value that it already has, which is 1 microhenry. So I'm going to set that to 1 microhenry. And then we can do the math for that. So we'll go to the calculator and do that math. So we said that the denominator was 4 times pi squared. So I'll just do pi times pi times f squared. So f is 100. 100 squared is 10,000. So we'll multiply by 10,000. And then times L, which is 1 microhenry. So 0.000001. Okay. So that's so 1 over that number is going to give me my capacitance. So the capacitance that I should use is 2.53 farads. So we'll go and enter that in our simulation. So I'll make this one 2.53 farads, and I've got 1 microhenry still. So that should give us a cutoff frequency of 100 hertz. So let's try it. So we'll run our AC sweep here. And there we go. We've got a nice graph. The cutoff frequency is right about 100 hertz. We can see that for every time the frequency increases by a factor of 10, the amplitude decreases by a factor of 100. Okay, so at 10 hertz, the frequency, I'm sorry, at 100 hertz, frequency, the magnitude would have been right about 1. When we go down to 1,000 hertz, the magnitude is 0.01. Okay, so it goes down by a factor of 100. Now, there is a problem here, though. Right at this cutoff frequency, we have this big, big peak. Okay, it goes off the top of the screen. It's bigger than 100 times the input. So if we put in 1 volt of an AC signal, peak to peak, our output voltage would be more than 100 volts peak to peak, theoretically. So that is a big problem. Usually we don't want that. Okay? So what we can do is we can add a little bit of resistance. Okay? So instead of just having a straight wire here, what we can do is we can put in a little bit of resistance, and that's going to decrease that big peak. Okay? So I'll put in a resistor. It only has to be a very small amount. Okay? So I'm going to start with a value of just 1 ohm. Okay? now let's run that AC sweep again and see what happens. Okay, so now that greatly decreased things. So that might have been a little bit too much, actually. So let's go back to our schematic and just make that 0.01 ohms and see what happens there. Okay, so that is looking much more reasonable. So we can make our maximum value here just 1. And we can see that the that we're getting much less of a peak there. Okay, so that is one way that you can decrease the amount of you can decrease the peak in your circuit. You can just add a small resistance, and that greatly gets rid of it. So that's a little bit about how you can create an LC circuit in multisim.